Hello, I think we're live now. I'm just going to wait for myself on YouTube, as usual. Hello, I think we're live now. There you go. And it sounds like I've got a good volume as well. So how's everyone doing tonight? And we're actually doing something a little bit different today, which is something I've actually not done in years. Jonathan Mattison first. Hello, Jonathan. How's it going, dude? Welcome to the stream. So let me tell you guys this story, right? So maybe 3-4 years ago, I was a massive sort of like hardware head. So I used to just buy like random hardware stuff, like a new Raspberry Pi Pico that just got released, and then try to program random shit into it. And I used to love Raspberry Pis, actually. They were by far my favorite like thing to play with, put it that way. I'm good. Gotta go though. I have work. No worries, Jonah. Thank you for joining, man. Just make sure you drop the like. That's all I appreciate for. Jonah, good luck. Thank you, man. Thank you. For you too. Have a good work, hopefully. And yeah, Raspberry Pis were by far my favorite thing to play with. And I've got like at least 15 of these guys here lying around. There's 2 of them here in case one of them burns, in case of like short circuit one of them, because they're very easy to short circuit, surprisingly. Welcome, goodbye. Indeed, yeah, welcome and goodbye. But the thing is, I've not actually done any of this hobby, shall we say, in quite literally 2 years. I don't know what happened. I just lost the interest. But I've got like a massive box here full of like LEDs and wires and, LCD displays that kind of need to play with, really. So I thought, yeah, let's do it on stream. Let's get back into it and see if I can remember most of the stuff that I did. So what are we doing today? We've got here a Raspberry Pi Pico, which is the first model, actually. I think it came out in 2020, or something like that. Yeah, 2020 it seems here. And this has a microchip, also by Raspberry Pi, called the Rpi 2040. And it's a very tiny kind of, it's not even a system on a chip. It's not a system on a chip. It's it's an embedded system, put it that way. It's just a processor with some pinouts, right? But we've also got here, I'm not sure if you guys can see, it should be there. We've also got this LCD display, which is I think it's a 140 by 140 SPI of the LCD display, right? So we can try and show things on it or control it through SPI with Raspberry Pi. So SPI is just a protocol for sending and receiving data over the wire, essentially over a wire. But we're not going to do too much of that because Raspberry Pi has libraries for it, so we don't actually have to understand it. But it's not a very complicated protocol anyway. So if you go home and search for it on Google, you'll find plenty of it. LCD on the breadboard, yeah. So you might have noticed as well that I've already wired everything up here. So this wiring here, like there's actually this bit here, right? So this is the actual chip I've got. The black stuff you see on the back here is the micro omnibus. So this is just something to allow me to connect like multiple wires to the same pinouts, right? It's just easier for me to play with it. But this has been done for like a long time. I've not touched the wiring at all because I don't want to mess it up. But it is something we're going to have to look at in this stream anyway, because we're going to make sure that the wiring is done properly, right? So there's nothing here on the screen now. It just turns on because there's power coming in. But yeah, we're going to start from scratch. First things first is we are going to try and install the SDK. So the Raspberry Pi Pico, obviously you have to compile C++ code for the Pico. I think GCC probably does the Pico now. I'm not too sure, but there is a CMake SDK you have to download here. So this is the getting started with Pico PDF that Raspberry Pi releases. You can read into it. So I'm just going to follow it for now and let's see what happens. So first of all, let's actually create a dependence, create a Pico SDK. Oh, I've already got the SDK apparently, but yeah, let's just create another directory here for the development. So I don't know, LCD let's say it's an LCD driver or something, right, that we're creating. We'll try and keep things very, very simple. Now, this has changed quite a bit from the last time I actually checked it, because it seems like they've got a Raspberry Pi Pico extension now. And this was not a thing back in my day. When the Pico came out, they barely had a working CMake SDK, which I actually had to modify quite a bit. But now they seem to have an extension. So let's try and just install that, shall we? Well, we're not going to look at that yet. So I want to see how well it integrates to things like CMake presets and whatnot. So yeah, Raspberry Pi Pico. Let's just put Pico in here. So what does this do? The official VS Code extension for Raspberry Pi Pico development includes several features to simplify project creation. Okay, let's try that. Hello, Slim. How's it going, dude? It's good to see you here again, man. The second time of the week you're joining the stream. Thank you for the support. And guys, don't forget, please like the video if you haven't yet done it. So this is the official Raspberry Pi VS Code extension, Visual Studio Code extension for Raspberry Pi Pico development. This extension equips you with a suite of tools designed to streamline your Pico projects using Visual Studio Code and the official Pico SDK. For a comprehensive getting started guide, for a comprehensive setup instructions, refer to getting started guide. Download the latest beta. We don't want that. I am always here. Thank you, dude. That's kind of a threat. That sounds like a threat, man. You're always here. So it's got project generator. Easily create and configure new projects, which with support for advanced Pico features like I2C and PIO. I2C is another wire data transfer protocol, I believe it is. Quick project setup, initiate. We're probably not going to be using this, to be honest. So well, let's try it anyway, right? So you can find the store entry, blah, blah, blah. When installation completes, check the activity sidebar, by default on the left of VS Code. If installation was successful, a new sidebar appears with a Raspberry Pi. Oh yeah, we do have that. That's pretty neat, isn't it? I like that. What is that? Micro Pico device controller, experimental. What is that? Your board must be connected to Wi-Fi for this feature to work. No, yeah, we don't have that. So if we do a new C and C++ project. Oh, this is cool, man. They've done this well. Like this is cool. So project name, LCD driver. Let's just try and follow it. Board type. Oh, this is the Pico. Just the Pico, no Pico 2. Wait, what's on Pico 2? RISC 5. All right, so this is a different architecture. Now location, let's change it. Change the development. And what did you call it? LCD driver. Okay. Select project, Pico SDK version. We'll select the latest one, I guess. Now we do want spy, but I'm not gonna initialize any of this because we're just going to copy it. Code snippets to demonstrate these features. We're just going to copy one of the LCD examples. Like Raspberry Pi Pico already provides an example to control this particular LCD display that you can see here. So yeah, we're not going to select that. We're just going to use that. STDIO support, console over UART, console over USB seems to be the one. Disables all the USB use. Okay, no. I don't know. What do we want? Code generation options. Generate C++ code, enable C++ RTTI, uses more memory. Use project name as entry point, file name. Yeah, let's go for that, shall we? Downloading and installing the SDK. This is nice. It does everything for you. You know, while this is, going on, let's see what else they tell us to do. Load and debug a project. Okay, so this is just literally what we were doing. The CMake tools extension may display some notifications at this point. So question, have you guys ever bought a Raspberry Pi? And a further question is, have you guys ever played with this one here, which is the actual microchip, not microchip, but the microcontroller by Raspberry Pi? Not quite, like it doesn't have an OS or anything like that. So yeah. Open blink.c to view the blink. Download and install CMake. We've already got CMake. Why is it trying to install it? Okay, so it opens a new thing. Okay, so LCD driver. So what does it put in my CMake? It puts a bunch of shit already in it, which is nice. I always wanted one, but never got the free time to think, so I kept postponing it. Yeah, that's what I did as well, man. I bought it, played with it for like maybe a few months, and then never tinkered with it again. Right, so this adds a bunch of shit that I don't know what it does. Do not edit the following lines for the Raspberry Pi Pico VS Code extension to work. Okay. So project. Okay, we've got ASM. I do wonder, like, where does this set the compiler and stuff? Because I want to see if this is doing the right stuff, right? So Pico SDK import. And this is a C file. Pico SDK lib. If I just build it, well, like, what do we get in the end? CMake build. Oh, there you go. So it does bring up a, like, it has already installed the ARM compiler that I need here. Okay, so fairly easy. Let me just close Steam. I'm sorry for that, guys. Just keep, like, getting pop-ups of friends and shit. There you go. So things build, and we should have what? The LCD file in here. Let's see, yeah, lcd.bin. I guess the bin file is what we have to kind of do, right? We have to send over to the Raspberry Pi. So one thing to do is, like, if you connect the Raspberry Pi Pico and you press the reset as you're plugging into the USB, you get this, right? So let's open my Linux in a new tab so we can pass in this binary file or copy it to there. I don't know what it does though. So std unit always sleep for that long. I want to see if debugging works as well. So home, myself, development, and we have LCD display, right? Oh, there you go, LCD driver. Okay. So this is the file we should probably be copying down to here, which is nice. Now, if we debug, like, do we already have? There you go, Pico debugger. So if I put a breakpoint here, does it actually work? There is no way it's going to, right? Could not start GDB process. Does the program exist in the file system? I don't know. You tell me. Does it exist? So if I had a new terminal here, GDB, it does exist in the file system indeed. Let's see what the launch.json file looks like. So this is where you define, like, how you debug things in VS Code, and includes, I guess, calls to GDB in here. Interesting. Let's try that again. Cannot start GDB process. Does the program exist? Error spawning GDB multi-arc. End. Okay, maybe GDB multi-arc doesn't exist, and that's a special GDB installation we need to install. GDB multi-arc. There you go. Ubuntu install. Hello, Robin. How's it going, man? GDB there you go. So then install. Okay, so let's try that one. Now we've got GDB multi-architecture. So perhaps if we do it again, GDB server quit unexpectedly. See the GDB server output terminal. Tab for more. Okay, GDB server on the output. Let's see if we can figure out why debugging isn't working, yeah? GDB server. Do we even have that? Where is GDB server output? Nope. It's not in debugging either. It's good. Just finished installing some new RAM in my computer and changed the thermal paste on my CPU. Oh, nice. Nice, yeah. I had to do that. I had to do exactly that for this laptop last year. Because I only had 16 gigabytes of RAM. And I couldn't really even like run Photoshop in a game on the side. Because it was taking up too much RAM. But I upgraded it to 32 gigabytes and upgraded the thermal paste and everything for that as well. Probably a small dot or an X. That is the question. You know, that's the real question. What kind of person are you? So Cortex debug with external OpenCCD. Let's just try that, I guess. Error exists after running debug anyway. Does it work? No, it doesn't work. Maybe there is no debugging today, guys, and we just have to run this. I do wonder, did it start though? So if I plug it on and plug it back in, it's all white now. I don't know what it's doing, but yeah. Let's see if I can get the blink code, right? So this is doing something I don't know. So stdio initializing all of the stdios. I'm getting a white screen now, so probably not working. This print is not really working, I guess. So yeah, compile GDB server. Oh, GDB server is here. We did find it. What happened here? GDB server session closed. Okay, it doesn't say why. Why it failed, I guess. Yeah, let's try and get the blink code, right? So, for those who don't know, this board has a little LED embedded to it. And we can get an example of the blink, right? So I think, in fact, if I look at the Pico, Raspberry Pi Pico examples, we should find a few of them that we can try and compile for it. May your thermals be mild under heavy load, and may your CPU last for many generations until it dies or find a better one. Yeah, I guess, yeah. What's the difference between a Pico and an Arduino? As far as I know, Arduino, I don't know. I think they're both the same, to be honest. Picos are just kind of a lot cheaper. Now, the difference between a Pico to a Raspberry Pi, a full-on Raspberry Pi, like the Raspberry Pi 4 or 5, is that it's just a microcontroller, right? Right, let's see. Where's that blink shit? Blink, blink, blink. Blink, there you go. So let's see if we can have this. It's doing a lot of stuff. I don't know, like turn the LED on and off. What? This is a lot more complicated than it used to be. Right, so if we just have that, let's try and understand this. Pico W devices use a GPIO on the Wi-Fi chip for the LED. So I'm building for Pico W. I guess this is the code for it, which we don't care. Right, where else is it? Okay, so this is just some, we don't care about that because we don't need it. And we don't care about that either. Oh, what did I do? Okay. Wait, was there a namespace here? What was it? In it, yeah. So we actually do need the function though. We just don't need the rest of it. Right. If and def delay, we define that, and then we need an indiff here that I've kind of deleted by mistake. Pico has Wi-Fi BT module like USB. No, not this one. The Pico 2, I think it has, but this is the original one. So the one I bought like 4 years ago. So it's just the wire, dude. Just the wire. Let's see. I am interested to know what the Pico 2 has, though. I think it has Wi-Fi for sure. So if we buy now, wireless, yes. Oh no, yeah, the Raspberry Pico 1 series. GPIO headers, yes. So Pimeroni is a good website. I always buy it from there. So Pico W. Pico W has Wi-Fi. Pico WH has Wi-Fi and the soldered headers as well. Hey, what kind of project is this? This is just I'm trying to control an LCD with the Raspberry Pi, but we're nowhere near that yet. Wireless is 0. Sorry, yeah, wireless is 0. Usually that's how Raspberry Pi models are. Yeah, I mean, this is, if you guys are interested and you're in the UK or Europe, this is the website that I use. It's pretty good. They have like everything to do with Raspberry Pis. I spend a lot of money here. Anyway, let's get back to it. So default LED, this is what we want. We don't want that. Set LED. And we can probably build this. We have built this. We now have, I guess, let's try and reconnect it and bring up. There you go. So you have to reconnect while pressing the reset button for you to be able to put things into it, really. So, all right, LCD driver is the one. And it seems like it didn't build. That was 10 minutes ago. That's not right. Let's rebuild it. Okay, yeah. I mean, the metadata for the files just isn't updated apparently by Windows if you're looking at the Linux files, I guess. Right, I'm not seeing any LED flashing, which is concerning, isn't it? While true, we should set the LED. Default LED Pico. What is that? Line 25. Yeah, so I do wonder now, is my Raspberry Pi fucked? What is going on here? Have I shorted it already? No, it can't be because... Yeah, it can't be. I don't know. It is recognizing it on my Windows, so it can't be shorted. So GPIO init, GPIO number, clear the output, enable, set the input, set direction, GPIO out, and return Pico OK. Does the power LED light up? Yeah, it should be. It should be lighting up, but I can't really see it. So what we're actually looking at is... It's like one of these two. Like right in front of my finger. I'm not sure if you can see her. Thank you. Dude, this guy just comes on the stream and says thank you every time. Like, thank you for what, man? Well, thank you for joining the stream and liking the video, but I've not done anything yet. You have to press a button while uploading it, if I remember right. Yeah, so you do that when you connect it, and then you bring up the directory here, right? So you can see it as a new like USB device, and then you just kind of bring it onto your folder here. But once you've done that, you have to press a button when uploading, if I remember right. Yeah, once you've uploaded it, then you can just kind of reconnect it, and it should be there. So you bricked it. That's what I'm wondering now. This is what I'm wondering because, yeah, I don't know. I don't know. It kind of sucks if I bricked it already. By bricking it, I mean shorting, right? Because that's what usually happens with these things. You short it by mistake by, I don't know, like touching 2 GPIO, like a 5 volt GPIO to another one. It's kind of annoying. But that's the reason why I've got a different one here. So I'm gonna try connecting a different one. For that though, I need to do some fuckery first. Fuck. Right. So I have a different Pi. Let's try and use that one. Oh no, this one is even more of a problem. I'll tell you what, right? Because look at the difference here. So this Raspberry Pi, I've soldered it myself, like the headers. But I soldered this one the other way around. So it would look like that, really. I prefer lemon pies. Yeah, I prefer lemon pies too. Oh gosh, what have I done? What have I done? No, it's not bricked. It's not bricked because I can see it here. It's just not blinking. So let's see. Maybe the GPIO number is wrong, right? Let's assume that that's what happened here. Have you tried turning it off and on? Yeah, many times, yeah. So to turn it off, I just have to do this. Yeah. And then connect it. But if you hold the button, then this happens, right? Then you get the upload option. This is why I think it's not bricked, because it is recognizing it here, right? It is. And then to actually run the code, you just have to paste it here. That is it. And it will run whatever binary file you have, as far as I know, unless it's a different one that we have to. We put the hex file as well. Oh no, I'm an idiot. It's the UF2 file that goes in there, right? There you go. Do you see now? I was just being an idiot. Yeah. So it's not the binary file, and you can see it blinking now. Great. We know this is not bricked, and Anton, you scared the hell out of me, man. You're scaring the hell out of me. So, wait, you guys can't actually see this. Wait, let me see. Wait, you still can't fucking see it. Why is my camera frozen? Like, no one told me the camera's frozen. How long has it been frozen for? Come on, guys. Yeah, you can't see any lights blinking because the camera is frozen. Let's try that again. That's the wrong one. Oh gosh, I don't like this angle. This angle is shit. Is it this one? There you go. Yay, can we get a heart emoji? Yeah, if that happens again, let me know. Like, I've been touching the Raspberry Pi all the time, and yeah. 4 minutes frozen. Yeah, I mean, why do I have viewers if you guys are not going to chat? But great. Now, the next thing to do, right? I'm going to be a very lazy person and actually look at some Raspberry Pi Pico LCD example, right? Because I know there is one somewhere because I've actually looked at it before, right? What's the black board under the Pico? This is a microbus, omnibus. So it just multiplexes the pin out. This is what I have here. So micro Pico omnibus. this guy here. So it just extends it. So like you can actually, you know, if you plug it in the right way, you can see what you're plugging things into. And it's just easier to work it with the Pico, really. You have to look for specific LCD code examples. Yes, I do. So I know for a fact that we have some SPI examples here that I've used myself. There is a library usually. Yeah, there's a SPI library. Now, the one I particularly need is this one here. It's for this LCD in here, right? Let me see if I can... Like, does it look blurred as hell? Like, well, how does it look for you guys? No, it looks fine, yeah. So this LCD has a particular model. I just need to find out what it is to see if I'm pretty sure it's BME 280 though. But the one I've got is actually... also from this website, I can probably just find it, is this one here, right? So 240 by 240, right? 240 by 240, yeah, it looks about right. This is the only one, right? I don't have another one that's the same. 1/3, yeah. Yeah, it is this one. It is 1.3, right? 1.3, yeah. 1.3 inches. So, without further ado, this is a SPI screen, and I'm pretty sure it's compatible to this one here, except you have to just, you know, kind of change some stuff, right? So this is probably what we're going to use. What have they got here? Oh, crazy, yeah. So I think this is probably what I followed as well. Let's see. And they also use different terminology here. So instead of like mastering like Mossy and Miso, they use different shit. So Mossy is master out, slave in. So master out, slave in. So going from Raspberry Pi. Which one is this one here now? What LCD model is it? There is a link on the product page and connections. Yeah, good question. So probably better if you read the connections. So there is a link, breakout hat with this. No, we don't want the hat. Python library, adapted existing Python library. No, we don't want the hat either. The easiest way to use SPI breakouts of Raspberry Pi is by plugging them into a Pico breakout garden base. No. Or a Pico garden. Okay. Breakouts using this. Pimaroni Pico examples. Yeah, this, I'm pretty sure this BME driver is the one we want, to be honest, because I've used it before. I vaguely remember the name, but I want to get some confirmation, to be honest. So Antonio Arai, I need to just find the wiring drawings. What is this? No. Find the wiring, make sure we have it right. Okay, no. Okay. It's on a product page. Am I missing that? Where is the product page? At the bottom. At the bottom, right? Product page. I'm just being blind completely. Connecting adapter Python library. Breakout hat. Dude, where are you seeing this? This is frustrating. I'm sorry. Where is the connecting to Raspberry Pi Pico? Right. So it is here at the bottom, you say? There. Hello, Muslight. How's it going, man? So it's not this one. It's not that one. Here's how he goes. Oh, yeah, I see. Yeah, I just missed it. I thought it was an image I was looking for. So, right, ground to any ground. Let me just make sure that we've got that. So we have ground, which is the black wire, to ground, yeah. Ground to minus here. BL. So it's CS to GP17. GPIO 17. So clock, I guess CS that stands for clock tick or whatever. 17. Yeah, GP17, that's right. Yeah, I think I followed this, to be fair. It seems to be right. So S. You have to open a board and pin out image. If pins are not marked. No, they are marked here. So we have like, this has the actual like markers. So everything that we see here actually corresponds to a, to a pinout. So everything here makes sense. SCK, which is the blue wire, that should be connected to 18, right? So yeah, that's what we have, I think. Yeah, we've got that, right? GP18, yeah. So Mossy, Master House, Slave in, GP19. And Mossy, in my case, is purple. So the purple wire is 19, yeah, that's right. And then DC to 16. Now DC is an interesting one. So DC is, ooh. Yeah, DC is on 16. BL is on 20. Yeah, okay, and ground we've already checked. Right, so this checks out. We have the right ones. Don't forget to do unpower a board if reconnecting. No, yeah. I've not reconnected anything, dude. I've I've bricked too many of these motherfuckers here to know that, so don't worry. Yeah, literally, like, I think I bought 5 of these when I started tinkering with them. And I kept bricking like one after the other because like I'm reconnecting shit, and then I accidentally shorted by connecting ground, by connecting like GPIO 17 to whatever 5 volts or something. And yeah, it's very easy. They're very cheap to buy, but also very easy to brick. Language, I'm sorry, yeah. I mean, I'm not sorry. This is not really a kids-friendly stream. We're not going for that here, are we? But yeah, so I am pretty sure with that in mind, the code for this thing here, so the breakout BMP should work. So we have stdlib, we have bmp.h, Pimeroni I2C. Oh, it says I2C though, not quite spy. Okay. First of all, let's get ChatGPT explain spy gateway. So I just want to see what these things are equivalent to, because what we have to do here is figure out like what we have here. So like SDI, what is it equivalent to? I mean, SC is fair enough. But SDI, SDO, SCK is the same, hopefully. So SDK. So yeah, we just got to figure out. Google your chip, your Pi chip model. Why? Oh, we know that already. So RP 2014. This is the Pi chip model. The data input and output. You know, I know what you're trying to get to. You're trying to get to the data sheet, but we've already got it connected here, and we should be able to use SPY on whatever GPIOs we have connected, right? Now, serial clock, SD slave. Huh. This is not the one we want. Spy flash master slave. Wait. Maybe this is not. How to interface Raspberry Pi, beaming temperature. No, this is a temperature. What the hell am I doing? This is a temperature sensor. Oh gosh. Yeah. This is not what I wanted. I am pretty sure that I've used something here though before. So flash. Maybe it's not going to be on spy. Maybe it's going to be under another directory. Blink ADC. Where could it be? Can we search in here? LCD display. LCD UART. SD. There you go. That's more like it. PYO, right? PIO. It's on the PIO. Pi input and output. So LCD. I'm pretty sure. Okay, so that looks promising. I'm just trying to remember where I picked the code from in the past. So maybe this might work. Let's just look at the C code and figure out. DC is there. Data input, I guess. 0 define. Okay, this feels like it might work, to be fair. Look by name ST7789. Yeah, we've got that now. I'm just not seeing the spy code here. Well, this is it really. You found it. Yeah, I found it. So what do we need here? So we need a bunch of stuff. Include hardware, Pico. Okay, so we need to copy these files as well, hopefully. What does that do? This is a header for some data, I guess. Okay. Okay, yeah. I mean, with that in mind, I do think we already have that in Pico examples. Yeah, Pico examples. So we have ST, whatever, LCD. We can copy everything here. Dot H C++. Does that work? HC to 1 down. We have another one. LCD driver. Okay, what do we have in LCD driver now? Didn't copy shit in there. Because this directory is there you go. That works now. Right. I guess the main... Right, so there's a bunch of shit here that we can't. File not found. Let's figure out what the CMake list said here. So that C file is the main target source. Pico generate PIO header. What is this? What is PIO header? So I have no idea. What's a PIO file? Does anyone know? I guess it's something to do with setting the pins. Interesting. Kind of looks like C code. Anyway. So what we're going to do is we're going to change this. So this is the LCD. And SD77A9 LCD.c. That is the file that we have. Enable UART. Okay, I don't know what that is. That's for debugging purposes, I guess. Yeah, I mean, does it build? Does it build? It doesn't build. I'll specify compile definition for target LCD driver. Yeah. Let's just change that to whatever it was so we don't break it. Okay, hardware.cpp, not found. Where is hardware from, though? Where is hardware from? This is where we've got to figure out and copy it now. So this is clearly from PIO, I guess. PIO. Let's see if we can find it. Maybe it's included here, right? So target link libraries, hardware PIO. Yeah, there you go. So we have to copy this target as well in here. So hardware PIO. Where is that? So if target that, we include this. I'm looking for the target link, add library call to it. It'll be here somewhere. And that's what we have to copy. Can't maintain consciousness. This old machine is low on power and the CPU needs to clear the cache. Gotta sleep. No worries, man. Thank you for joining, man. Just make sure you like the stream. As usual. You know it. You know already. Where is this target created? Come on. Where is it? So, add library. Hardware. Is that a thing? No. Interesting, though. We're really not going to find that. There you go. If target hardware PIO. I just don't know where it's found. Where is it? Where do I have to copy from? These are all linking against it. None of them are creating it. It's an SDK library. Provides simpler or better interfaces for all these operations. Tell you what. This should be working then, right? Because if this is in the SDK, we should have that already. See, we have hardware there. GPIO. Input output. Maybe it just got renamed to GPIO. Is that correct? Wait, what are we expecting here? Yeah, what I think is happening is like the Pico examples that I have are out of date, right? It's PIO if I remember right. Yeah, so what I think is happening is I just have outdated stuff, right? So if I look at, for example, the LCD again. Oh no, PIO is there. Okay. Should we just see if we can like just clone this and then build it all? So last updated 3 months ago. That's fine. So remove .rf, Pico examples. Let's just clone it. Does this have a CMake list? Yeah, it does. So we should be able to do it. Open Pico examples. And yeah, make it work, I guess. Start a new project with it. There's a VS Code plugin for Pico and it includes PIO if I remember right. Yeah, I already have that, by the way. I've got that installed. That's how I created the project we were just doing now. All right, so what I think we have to do here is like click on that and import a project. Oh, import a project from example. There you go. Maybe we can do this, right? Select an example. If only this worked. SD. Oh, there you go. PIO. Oh, beautiful. Yeah, I see what you mean now. Yeah, absolutely. So let's change the location here. LCD. If we select that, wait, so debugger, debug probe, default, show advanced options. So do we have the right? Okay, that sounds about right. You need to create a folder. Okay, now we have the Pico. That's all that matters to us. Just having that the Pico selection on the compilers is the most important thing. They really made it easy, to be fair. It didn't used to be this easy. You need to create a folder. I read that again twice. Sorry about that. And yeah, you don't need to create a folder because I think they just place whatever projects you create under the one you select. So you have to select the outer folder if it makes sense. That's how it seems to work. Right, so yeah, this works, you see. So it seems like PIO does work. Now this is the interesting part. So screen width. Was it 240? I can't remember now. I think it was. You need to create a folder. Again, I'm reading shit twice. So DIN. What is DIN? Right, this is interesting now because we have to. On the right panel, you have a Pico button to upload. On the right panel, you have a Pico button to upload. Cannot see that, to be honest. Import project, run project, configure, clean. There is a debug project here. Maybe we can try that one out. Yeah, so this is where I kind of select the right pinouts, right? So what is that supposed to be? Run project. Yeah, I'm just not sure if it's going to work out of the box with this pinout. I was just trying to see it. Yeah, yo, yes to default. I don't know which one. So no accessible RP series devices in boot cell mode. So I guess what we have to do is we have to reconnect With the, yeah, the button. That's right. So we run project. No accessible this. Okay, interesting. Terminal will be reused by tasks. Press to close it. Nah. Restart task. Failed to terminate and start. Okay. So it didn't go into run mode. Let's try and debug it though. Cortex debug. Does it work? DB server quit unexpectedly. Oh gosh. DB server, what's the actual error here? Expecting NM next to object dump. If that's not the problem, please report this. Yeah. No. It seems like we can't debug it either. So I guess the only option we have is to kind of compile it, right? So the only thing we can do is compile it and then kind of just copy it. So if we copy the UF2 file into here, with a bit of luck, it will copy the file and things will run, but I'm not too sure. Why is it not copying the file? More details. Calculating. An expected error is keeping you from copying this file. If you continue to receive this error, you can use the error code to search. The volume for a file has been externally altered, so the file is no longer available. Okay, let's just try again then. Yeah, see, so the looks like you have to press a button and reconnect. No, I don't think so. I think it was just that the file changed somehow. Yeah, this is not going to work because we have to kind of figure out the pinouts here, right? So I guess this is where we open the Raspberry Pi Pico pinouts and make sure that I've got the right ones. Where are we? So getting started with that. Let's see where the pinouts are. Appendix. Copy pinouts from project product page. Pinouts. See, the problem I have here is that these numbers, so 0 it's not the equivalent to GP0, I don't think. So I'm trying to figure out if what I have to put in the define there. Is pinout not a thing? Pinout. Nope. Let's mess with it in a bit. So Raspberry Pi Pico pinouts. PDF. Okay, good. So what do I have here? I will look up for pinout image in Google. No, I've already found it, dude. Thank you very much. They like Raspberry Pi is very good at providing like all the documentation you need, to be fair. So the one at the very end, this one here, this pinout, which is GP0, right? GP0 is connected to, oh, let me just see it again. The third one, which is DC. So DC0, is that correct? DC0 for me. Let me just replace some of this actually. I'm going to put the ones that I have actually modified, what the hell, in here on the bottom. So this is 0 for me. Then what we have here, then we have the second one, which is GP17. This one here, right? Oh, no. Gosh, I have this the other way around. This is what I have. So in other words, that was wrong. now I can see what I have, and this one, which is 21 or GP16, is connected to DC, right? So that is the first thing I need to do. So 16 here, fine. And then 17 is connected to CS, right? Just making sure. GP17 connects to CS. This is by RX. So what does RX stand for in this case? We have CS, which is fine. So CS17. Right, so 17 is the one. Now what else do I have? Now blue, which is GP18, is connected to the third one, SCK. So 18 to SCK. I've got that here, 18. Yeah, I mean, it does match whatever it says here. So the SPI stuff is working fine. SCK. What is SCK? What is that meant to be in here? Look for colors also to understand it. Yeah, I'm looking at those, dude. So what is SCK in this case? Is it DIN? What's a different? Is there a different name for SCK? SCK clock selection. So I guess this is the one, right? I'm assuming that this is the one. So 18. I'm going to put a question mark next to it because I don't want it to compile just yet before I check. And then we have 19, which is on master out slave in. So Morsi. Data input, I guess. That would be 19. Chip selection, probably. Yeah. Chip selection. So clock selection, chip selection. Well, we'll see if it works in a second. And then we have the white one, which is BL, and that is on 20. So BL is 20 here, and we're certain of this one because it has the equivalent name. Then we have the pin reset. I don't know what pin reset is. Yeah, I mean the other ones are just so we have 1, 2, 3. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Reset probably ground. It's not quite ground because I do already have ground. I don't think I have to select ground in here, right? It just goes straight to ground. Like there is no GPIO setting up on now. Same with the 3.5 volt input. So I don't connect those. I am kind of looking pin out. Reset. No, yeah, I can't see a reset in here, to be fair. You see my ground is on this. This is for the ground for the LCD. That's where it's connected to. And the 3.5 volts is connected to this one here, 3 out. So those two, like there is nothing in, wait, I mean, don't touch connections. Yeah, I'm not touching connections. So those two are already connected and fine, I guess, right? Now, I wasn't sure about these two, right? So I'm gonna guess they are correct. If not, we can switch them and try again. But let's compile the project and try again, right? So if we disconnect it, fucking hell. We've got that. You got L file. I mean, don't touch the connections. You got L file. Yeah, I've got the UF2 file that gets generated. So this one here, that's the one you should copy, I think. Okay. You see, that works. That works. That works quite well, actually. Too well. So we made the right assumptions there. Now let's try and understand the code, because this is the hardest part. Wait, can you guys see it? Oh yeah, let me figure out here. Maybe it's just too much for the camera. It is. Oh, that sucks. But I can see a Raspberry Pi logo basically. That's what we see here. Maybe if I swap it so it's kind of like not directly on the camera, but a little bit there. Right? Maybe it'll work. Right. I mean, it's working. I mean, super. Raspberry Pi logo. So we made those assumptions correctly. Yeah, it's rotating. Nice, yeah. Good. Now let's try and understand the code, because this is probably knowing how embedded systems engineer code things. It's probably so complicated we won't be able to understand anything. First of all, where is the image data? I guess this is the image, and the data itself is here, right? So this is just the data generated from the image. So 256. So how many elements do we actually have here? So I'm expecting this to be the actual image data. I'm just going to check that we do have that. So it's 255, or is it, what is it? 255? 256 times 256. 65,000, right? But we have 100 and... yeah, it's probably 131,000 here. So how does it work? It's not an RGB, right? So how did they get to this number from this many pixels? That's the interesting part. Because if it was RGB, I'll do it by 3. And this is how many I would expect to have here. But it's not quite right. For sure. Attribute aligned. Do we have like a size of this somewhere? Is there a size? No. Yeah, so I'm pretty sure this is the image data. I just don't know how it's encoded at the moment. It might not be RGB. Because I was assuming it's going to be like a byte for each one of them. It's probably not right. Now, let's look at main and try and figure out. So std init, all this is just doing, what is it doing? So initialize all of the present standard std IO types that are linked into the binary. Call this method once to set up your clocks to enable this std IO support for UART or USB. Okay, seems like it's for debugging purposes, which is fine. So PIO. What does PIO stand for, by the way? Pin input output? Yeah, I'm not too sure. Not too sure. I'm gonna guess it's like pin out stuff. Pico in output. All right, fair enough. So the same as the GPIO, because there is a header called GPIO as well. PIO add program. PIO LCD program. What is that though? PIO 0. What is that? Identifier for the first PIO hardware IO instance for using PIO functions. Yeah, I don't understand what PIO is yet, but I guess we'll figure out. Let's see if GPT or something else will help us. First of all, on the official guide, PIO, is there any mention of it in there? Only GPIOs. So Raspberry Pi, Pico, PIO, instruction set. What does that do? Let's see if we can find some explanation. Developing programs for the PIOs is extremely challenging due to its highly specialized instruction set with a lot of parallelism, by all means intended, but complex, side effects. Debugging PIO programs directly on the Raspberry Pi 2040 chip is, in practice, technically rather impossible for multiple reasons. So it seems like it's just a way to write assembly for the pinouts. Interesting. On Pico. It doesn't really explain it. Most notably because of lack of access onto the PIO's internal state from outside. However, emulation of the PIO's core functionality can be perfectly tailored for support in developing and debugging PIO programs. A tiny but typical PIO program. PIO programs are usually quite short, but they're tight. They're tight and therefore usually tricky functionality requires high expertise in development and debugging, which I don't have. Instruction set. The set of instructions highly specialized on bit manipulations rather than general purpose computing and on single cycle precision time. Specifically, the instruction set does not support any arithmetic operations except register, decrement, on jump instructions. Does not support any logic operations except bitwise complement move instruction. Rather, conditional jumps that only support test for zero status and register equality. What is the point of this? How does this differ from GPIO? That's my question. Programmable input and output. Okay, yeah. So this is what it stands for. So like other modern microcontrollers, the Raspberry Pi Pico incorporates several standard interfaces. So UART, SPICE, I2C, IC Square, I guess, allowing it to easily communicate with a wide variety of peripherals. But the Rpi 2040 differs from other microcontrollers because it incorporates programmable inputs and outputs, PIO, allowing you to create your own interfaces or to implement specific interfaces that would be managed natively by the Rpi 2040. A great example of using PIOs is interfacing NeoPixel LED strips, as well as we will see in this article. Okay, so it seems like you write programs for the GPIOs, is that correct? The Rpi 2040 incorporates two PIO blocks. Each PIO block is comparable to a small processor which executes the code independently of the CPU. Okay, you could draw on display using Pico display library from the same repo. I guess, yeah. I'm just trying to understand how this code works first, so then we can see if there's like a better way of doing it. Highly unlikely though. This seems to be like using the specialized programmable input and output, which sounds interesting. So it's like it's something that doesn't really happen on the main CPU of it, from the looks of it. Each PIO block is comparable to a small processor which executes the code independently of the CPU. It kind of sounds like an interrupt kind of thing. The PIO does make it possible to manage the inputs and outputs in a deterministic way, the timing being very precise, whatever CPU load. Ah, I see. So this is a way, I kind of get the logic of it. So this is a way to independently run some code that controls, for example, SPI devices or I2 square or I squared C in a way that the CPU cannot block the rendering, shall we say. So therefore, programmable input and output will execute in parallel from the CPU. That is interesting. Interesting indeed. Each PIO block is made of 4 state machines which can independently execute small programs whose instructions are stored in a shared memory, instruction memory. At each system clock cycle, each state machine fetches, decodes, and executes an instruction. Each state machine is used to manipulate GPIOs and transfer data. The programs are written with specific assembler composed of 9 instructions. Jump, wait, in, out. Okay, so this is the assembly that we have for it. Now, is this what this file is about then? Because we have this file here, PIO. We have this file called PIO, and I guess that's what it is. It's just programming the programmable input and output stuff, right? So for example, let's take a look. CSTD program init. So initialize the program in C. For optimal use of DMA bandwidth, we would use an auto-pull threshold of 32, but we are using a threshold of 8 here, consume 1 byte from each first in, first out entry, and discard the remainder to make things easier for software on the other side. I have no idea what this means, but anyway, so you can see that there's some assembly here. Interesting. And is this mentioned at all in here? Yeah, so wait and out are both in here, right? So out and no op, I guess. Yeah, no op is not mentioned here, but I guess it will be part of this. Okay, interesting. On the Rpi 2040, all 30 user GPIOs can be used as programmable input and outputs. Okay. So this is what the state machine kind of looks like. I have no idea what FIFO is. First in, first out. Kind of sounds like a stack kind of thing. Also, yeah, a queue kind of thing. I don't know what state this machine's hold. No idea. But cool. I mean, example, generating a square wave. Cool. For the sake of simplicity, our first program will be written in MicroPython. We want the PIO to produce a square signal on the GP28 output. Okay, so high or low, and then it's just square for whatever frequency they're doing, right? So a square wave. The system clock frequency is 125 megahertz by default on the RP20. State machines run at the default system clock rate. So these state machines run at the default, whatever, at the default frequency. We are going to program a state machine so that it sets the output to its high state for 32 cycles, or however, 256, I guess, right? Nanoseconds. One cycle is this. So you times that by 32, okay, which is 8 nanoseconds. So it's this many times per second. 1 over that per second is 8 nanoseconds. So 32 times that is 256. Okay, makes sense. And then sets the output to its low state for 32 cycles as well. The square wave frequency will therefore be this. Okay. Right. So this guy is just teaching us how to do the PIO stuff now. It's a little bit weird, but like I'm definitely not high, and this text looks funny. It just looks fuzzy. So it specifies the start location of the program loop. Test the output of to the highest state, instruction executed in 1 cycle. It remains in this state for 31 cycles. Set pins 0. Here's the code written in MicroPython that will transfer to the Raspberry Pi Pico, and which will program the PIO state machines as we have just defined it. Let's see, so def blink wrap target. I don't know what this is, but there is a decorator here for ASM PIO set in it. PIO, okay, out low. I don't know what wrap target is, but the same thing is mentioned in here. So wrap target is there. Store here if no data. Let's see. So you can do that in Python as well, which is cool. We observe a square signal on frequency. This, okay. It is possible to modify the frequency of the square signal by varying the number of cycles during which the state machine leaves. Okay. So it just looks like a very precise way to control timing in the GPIOs, right? Because if you're kind of programming the GPIOs in, let's say, normal Python or normal C++, you just use the GPIO headers, and you want to turn like a pin on at a precise time, that might take some time. And then your CPU, you might be running things that are non-deterministic anyway, so your CPU might be blocking on certain things. And this is a way to kind of do that separate from the main program and make sure that your timings are immaculate, which is cool. It definitely can be very useful for things like audio programming, I can see. And in the case of this the SPI LCD, it's probably just because of the SPI protocol, right? Because things have to be very timed very strictly with the clock, put it that way. So yeah, I mean, I can understand what it's for. I don't really know how to use it yet, but at least we can figure out what some of this does, right? So this probably gets a state machine. Like there's 4 of them according to that. Oh, there's 2 of them only. So yeah, so this is not equivalent to a state machine. PIO hardware 0. So there's 2 groups of them apparently. Yeah, no clue. That article just said it has like 4 state machines. So I would expect that this PIO 0 to also be one of 4. But it only seems like it's 2 of them, which is fine. Right? So 2 groups. Next 2 groups. Where did he mention? There you go. So each PIO block is made of 4 state machines. Oh no, each block is made of 4 state machines. But I guess there is 2 blocks, right? So maybe this one and this one. I don't know. So each side is a PIO block. Is that correct? PIO 0 probably stands for core 0. Probably, yeah. There you go. The RP20 incorporates 2 PIO blocks. Each PIO. Yeah, so I'm guessing that PIO 0 is actually the first block, and the second one is the second one, right? 2 instances of it running. uint sm. Right, yeah. So sm, no idea what sm is for, but we have a function here. So offset PIO add program. Okay, so PIO add program. Let's look at the documentation of that. So attempt to load the program. PIO, the PIO instance, so it will be PIO 0 in this case. And the program data, is that correct? The program definition. So this is, so we have this from somewhere, from the header file. So it's a const struct PIO program. Wait, what? So static const struct. This is C. This is C I don't understand. So this is an anonymous struct from the looks of it. Which is called PIO program, right? So this is not actually defined. Oh yeah, no, it is. It is defined somewhere else. Ah, okay, yeah, because in C you have to kind of put, it's a type def struct here. Yeah, I just hate the way C defines structs, to be honest. Just not intuitive at all. But LCD is of type PIO program and has these instructions. What are the instructions? Yeah, so this is basically the same as what we have here, right? Interesting. The length is 2. The length of the program is 2. And the origin is -1. I don't know what that means. PIO version, whatever this version is, 0. So without going too much into detail, it just seems to load the program into the first block. That's what it does, right? The PIO program. I don't really know what the PIO program does. It would be nice if I knew, but it's probably going to take me a lot longer than this stream to understand it. So we're going to move on. So then we have, yeah, we've kind of seen this. The data pin is there, clock pin. Yeah, so it needs a few of them, right? So for optimal use, DMA bandwidth, we would use an auto pull threshold of 32. Oh, wait a second. So this is a generated C file from this. So this is just, yeah, okay. So somehow the Raspberry Pi Pico takes in this PIO file and generates the header for it. Right? So like, for example, the C stuff is kept the same. Like this stuff here is the same, right? So I'm guessing that in the CMake file, there will be a PIO mentioned here. Project that, add executable. There you go, PIO header, generate PIO header. Cool, cool. So it takes that thing and then generates this. Interesting. Anyway, so it actually does add quite a bunch of stuff in here, right? So CSDK and there. So this bit until the very end is the CSDK shit. So basically the bit above this comment is the auto generation. So all this stuff is auto generated. Just a simple clock serial. In other words, all of this is auto generated. What does he actually do? Yeah, I guess the important thing is generating these functions, right? So it's kind of like an assembler at the compile time, at the configure time of CMake. Because this is what it does. So the wrap target is converted to this. Right, cool. And somehow, yeah, it takes a bunch of stuff. We already had that in there. And then we initialize the GPIOs, set direction, so GPIO out, GPIO out. We have no input GPIOs, right? So clock selection. I don't know what DC stands for again. Reset, I don't know. If I... Looks like initializes pin configuration and adds a PIO block instruction. Yeah, it does. It does. An LCD in it would be an interesting one. And then we, okay. Yes, chip selection. Or clock selection. LCD in it, right. What does that do? LCD write command. Okay, this is the actual library that does all the talking to the LCD. And yeah, I mean, there must be like a massive little protocol for this LCD, right? So you must be able, you must have to send like particular commands to initialize it and whatnot. Not going to bother too much with this. We kind of know what it's kind of doing. Okay, other SDKs. Static image on screen, lame, boring. Raspberry Pi Pico. Spinning image on screen, bold, exciting. I want to get, it would be nice if we can get like bouncy balls on it. That'd be cool. I agree with this, yeah. Their example is very exciting. So lane 0 will be coordinates, bits 8 to 1 of address offset. Lane 1 will be U coordinates, UV coordinates, bits 17, 16, address. Will represent coordinates with 16 fixed point. Okay, this is, I kind of know what they're doing here, but I don't really understand it, if it makes sense. Right. They're using UV coordinates somehow. Unit LSD. See what I mean? See how difficult this is just to understand what it's doing. I just knew. I just knew that this example is going to be very difficult to understand, even though it doesn't need to be. So I guess our plan is to make sure that we can turn this into something a little bit more understandable. Right? I'll be happy if I can do that. So lane 0. I don't know what lane is. Interrupt config. Let's see what that function does. Get a default configuration. Interrupt config? A default interpolation config, right. Where is this from though? This is in the hardware interpolation. What? There's hardware interpolation of data. Interesting. Interesting. So interpolation config set shift. -1 because 2 bytes per pixel. No idea. Interpolation config set mask. Dude, like, are you guys getting this? Because I am not. I am not at all. Interpolation config set raw. So that they set a bit shift in here, and then they set a mask with some random thing, which I don't know what it does. It's code for rotation, I guess. Yeah, I guess it's code for rotation. It does make sense. But it would be nice for them to explain, like, okay, this line is whatever. Yeah. I mean, they do have some explanations here, but it's just not a nice explanation, I guess. Add full accumulator to base with which pop. So interpolation config lane 1. Okay, you see, so that log image size. What's the log image size? Yeah, this is magic, basically. This is code for someone who knows how to do everything, like image rotations with, I don't know, very low level code. I mean, if I was doing it, I would probably do it way less efficient than this, but you might be able to understand it by having like the RGB array for the actual image, and then, yeah, using rotation matrices to actually do the rotation. I guess this does the same thing, right? But yeah, it's geometry math. Yeah, it's geometry math for sure. But I mean, I know geometry math and I can't understand this. That is the thing. So main. Yeah, so it just seems to me that this interpolator object thing is like a hardware thing you can set. And then you set the state, and then we'll do some interpolation on the data or some transformation on the data, right? Just to make sure. What do we have here? So file interp. Each core is equipped with 2 interpolators. So this is the hardware PIO stuff. Okay, yeah, this is still in the hardware PIO. Each core is equipped with 2 interpolators, interpolator 0, interpolator 1, which can be used to accelerate tasks by combining certain pre-configured simple operations into a single process cycle. Oh, that's cool though. Yeah, that's why it's difficult, to be fair. Yes, it's for performance. Intended for cases where the pre-configured operation is repeated a large number of times. So if you're doing any sort of like, I guess, operations many times, which we are doing, I guess every pixel we're doing some sort of rotation to it, right? Then this becomes useful for that. This results in code which uses both fewer CPU cycles and fewer CPU registers in the time critical sections of the code. The interpolators are used heavily to accelerate audio operations. There you go, audio operations within the SDK, but their flexible configuration make it possible to optimize many other tasks such as quantization and dithering. I don't know, I never know how to say this word. Table lookup address generations of affine texture mapping, decompression, and linear feedback. It sounds very powerful. It sounds really powerful. It sounds like something we should probably read into a little bit more as well. Please refer to appropriate RP series microcontroller data sheet for more information on the hardware interpolators and how they work. Yeah, we can do that. Shall we do that a little bit? I'm kind of really interested now. So RP 2040 interpolator. Dude, Cornell University always hits. Whenever I look for something and it's on Cornell University, you just know that the professor who wrote this did a very good job. So the RP 2040 has 2 fairly specialized interpolator hardware modules, interp, for each M0 core. The advantage of using the interp is that each unit can perform an add, shift, bit mask, and a second add on each CPU's clock cycle. Data paths are set up by configuring registers. So this whole thing just sounds like it's some sort of like built-in FPGA. You just like reconfigure it on the go. The setup requires bending your brain. The setup requires bending your brain to figure out the intent of the interp design, which seems to be motivated by repetitive table lookup and interpolations. Yeah, I agree. I definitely have to bend my brain to understand whatever I just read here. There are two special configurations for the interpolators. Interp 0 can be put in blend mode, and interp 1 can be put into clamp mode. The examples below use both modes, plus the basic table lookup capabilities of the interpolators. Weighted average of two audio signals using blend mode. Now, this is a cool example. I like this. This example crossfades between two audio waveforms in real time to show a very basic use of the interpolator blend mode. Interpolator 0 is set up in default blend mode, except signed arithmetic is turned on. Two DDS units synthesized of sine waves, synthesized sine waves of settable frequency and phase. The interpolator adds two sine waves weighted by the value of alpha, which sets the blend according to, so the output frame, the output frame would be sine sample 0 n plus an alpha of sine sample 1 n, which is the second sample, I guess, minus that one. At time n. The image below shows sine 0 set to 200 Hz and sine 1 set to 600. So he just adds them together from the looks of it. The entire synthesis is 8 lines of code in a 40 kilohertz ISR. The sine wave tables are 15 by 16 fixed point, but since this is a integer type, the interpolator blend function just works. I want to see what the code is. How did it do this? Let's see how interp kind of works in this case. Set up the interpolator 0. Interp 0 base 0. Interpolator for DDS. Interpolator config, interpolator default config. And then we set the blend of the config to true, set signed to true, sign addition. And interpolation 0, set config. Interpolation set config to signed true. Wait, what? Could you not have done everything in the same step here? I guess there is a second interpolator as well, or maybe not. Oh no, it's just one interpolator that he uses. Yeah, so how is that actually used though? How is it actually used? So we accumulate alpha. Interp 0 base 0 equals sine 1 sine 0 and then the sine 1. There's two bases. What is the base? I don't know what the base thing is. I guess they're just like two random arrays you have to use. Is that correct? Base. Yeah, there you go. So type def struct base. It has 3 bases. Yeah, I still don't know what a base is. I'm guessing it's just like an array you can use to store data. And the accumulator, which is also, I guess, in here. Yeah, there's 2 accumulators. Accumulator 1 is equals to alpha. It doesn't look that difficult to actually figure out if you're trying to use the interpolator though. But yeah, it's cool. It just looks like a way to do really efficient, like repeated calculations if it's simple enough, right? like in audio programming, where he's basically just summing up two different waves there. That's cool. Going back to this, what do we have? What else do we have here? So yeah, the LCD code does a bunch of interpolator shit, I guess, to rotate the image. I'm guessing that's what it does. And then we have theta here, so right. Ah, okay, so UV coordinates. So, okay, yeah, I see. And this is the actual rotation stuff, where he uses the interpolator to accumulate stuff. There you go. So somehow that magically, we do have some maths here that will... Now this is the actual loop that's rotating all the image, right? And drawing it on the screen. Let's see if we can understand it. So this is the rotation angle. So basically, I guess if the theta is 0 here, the theta plus that. And then, okay, yeah. So we could make it faster by basically or make it slower, like by doing something like this. And if we build it, and we reconnect, then we're going to see that the image is actually quite a bit slower. There you go. It was difficult to to remove this. Can you guys still see it? Right. Now you can't see anything, but if we now F5 that, make sure the metadata is new. Yeah. There you go. So it's a lot slower now, and that's just, quite easy to figure out that this is equivalent to the shift in angle for rotation, which is fine. Can you guys see it? Yeah, you can just about see the LCD there. I'm sorry about that. But yeah, this is the actual rotation mathematics here. So rotate 4, this is just the rotation matrix, right? Yeah, there you go. So you recognize this from linear algebra if you guys ever done that, where you rotate things. So the first one here is what gets times by, well, this is the calculation of the U component. So you do the current U times whatever this is, plus the current V times that. And then the same thing for W, for V in this case, right? He's using UV coordinates in this case. And interestingly, it's int32 though. How do we do? How is it doing that with? How are they doing this with integer arithmetic? Interesting, isn't it? So we're just casting it to an integer, which obviously gets rid of some of the... Wait. Yeah, it gets rid of some of the precision here for the float, because this would be a float. Yeah, sine float. Call to undeclared library, sine f. Yeah, so cosine float, that's what the f stands for, and sine float. Times this unit LSB. So least significant bit unit. What is that? There is some shift here. I really don't understand what this, he's just getting the coefficients for the rotation matrix, but at the same time he's transforming that to somehow an int32, right? And I don't understand the logic here. This is usually done with floats, but clearly, yeah, I don't know. I have no idea. This is just getting a rotation matrix in integers from the looks of it. And it has to be an integer because then we're obviously putting those into the interpolator, right? And that is probably an integer. So rotate 0. So what is he doing? Rotate 0, which is this one, and then rotate 2. and the accumulator 0, and the accumulator 1 there. Yeah, I mean, I can't say I understand this, but it's fun. It's fun to try and figure it out, though. Yeah, so this is clearly, I'm going to put a comment here. So how do we convert the flow coefficients to integer? How does the shift? Should we try and see if ChatGPT will understand it? Because chances are, if this guy if this person has written this, they probably copied it from somewhere else, right? They probably copied it from someone who teaches, or some article that teaches you how to do the rotations in integer. Explain the following C code in the context of rotation matrices and integers. So yeah, this C code snippet constructs a 2D rotation matrix using fixed point arithmetic with integer values instead of floating point numbers. Yeah, so this is a standard 2D matrix. We know that. In a floating point implementation, you could store the values in the floating point numbers. For example, float or double. However, in embedded systems or performance-sensitive application, floating point operations can be slow or unavailable. Yeah, which is what they're doing. They're transforming it to integer so it's faster. Instead, fixed point arithmetic is often used. Okay, that latex notation has completely failed here. So the code scales the cosine and sine values by a factor of 2 to the unit LSB before casting them to int 32s. So yeah, I guess it doubles it as many times as unit LSB is, right? So it just bit shifts everything by 16 bits, right? Oh, no, it times it. My bad, yeah, it times it by 2 to whatever that is. Like, dude, what is wrong with the latex rendering? Someone tell ChatGPT, well, OpenAI to fix it. So cos theta returns a floating point between -1 and 1. Yeah, we know that. Multiplying that scales it up. Casting to I32 converts the floating point value to an integer, effectively storing a fixed point representation. Yeah, I mean, I don't understand this bit though. This is what I wanted it to explain. So like how scaling it by that will represent a fixed point representation of the floating point. Similarly, sin f theta is processed the same way. Purpose of scaling this. Oh, there you go. It does explain it. I'm just impatient. This technique allows integer arithmetic to approximate floating point rotation calculations efficiently. The trade-off is that you must handle fixed point precision manually when performing calculations. For example, when applying this matrix to a point xy, I wish this worked. It doesn't. I hated division too by that, often done via bit shifting, correct the scaling introduced. Yeah, so it just seems like on the other side, you just have to bit shift it. Give me the source that explains the above in depth. Okay, let's try this one. I am not reading about fixed point arithmetic on Wikipedia though. That sounds too boring. And what is this website? Jesus Christ. I could write this article with my eyes closed and it would still look better than this. Floating point arithmetic can be expensive if you're using an integer-only processor, but floating point values can be manipulated as integers as less expensive alternatives. One advantage of using high-level language is the native support for floating point math. This simplifies the task programming and increases the accuracy of calculations. When using a system that includes a hardware floating point math unit, this can be a very powerful feature. However, if floating point math is used on a microprocessor that supports only integer maths, significant overhead can be incurred to emulate floating point, both in ROM size and in execution size. Yeah, so in our case, I mean, obviously the Raspberry Pi Pico does support floating point arithmetic, but my guess is that the interpolators don't. So the interpolators are some like hardware feature that only supports integers, right? That's probably what's going on there, and that's why they have to convert everything to integers. The alternative used by assembly language programmers for years is to use fixed point math that is executed using integer functions. This article will discuss a method to implement fixed point math in C. Fixed point arithmetic. We know what that is, right? Everyone knows what that is. For instance, 16 bits, where the most significant 8 bits are the integer part and the least significant 8 bits are fractional part. We all learned that at university. If you haven't learned it, just Google it. Yeah. Unfortunately, C does not provide native support for fixed point. Yeah, no language, even C++ doesn't support fixed point. Doesn't support fixed point functionality by default. You have to do it yourself, which is annoying. The first step in the fixed point math algorithm is to initialize the system. This step defines the parameters used later in the development of the system. To illustrate each step, assume that your application requires a variable that ranges from 0 to 1 with granularity of 0.01. Another variable family that ranges from 0 to 100 with granularity of 0.1. And a third family that ranges from -1000 to 1000 with granularity of 0.01. The steps are performed as follows. Okay, so this teaches you how to get the scales, I guess, right? Second, the number of bits are required to store this number such that 2 to the x is more than n to the x minus 1. The number is to be signed, add 1 to it. For example, requirement x is 7 and 11 precisely. Yeah, I am going to learn more about fixed point arithmetic though. My mind, I'm not going to lie guys, my brain is kind of going already. So what I'm going to do is, I'm going to continue this maybe in the next stream. In the meantime, I'm also going to learn quite a bit about these things. So I want to be able to modify this and turn it into something like that's a little bit more pleasurable to look at. So shall we say that? Maybe turn this whole C stuff into a C++ code base, because this is all written in C. And we don't really do C, we do C++ here. That could be a first step. But I'm going to call the stream here. And thank you all very much for joining. It has been a pleasure learning with some of you. Thank you very much, Anton. It seems like you like this, dude. So I think you should definitely pick up a Raspberry Pi Pico, because you might enjoy it. You'll definitely enjoy it. And they're very cheap. They're very, very cheap. I think these ones cost something like £2.50 each. Let's look it up, shall we? The website I was using is Pimaroni. I have one. Oh, you have one. Nice. Yeah, so I bought like a bunch of them when they came out from here. So are they still bestseller? There you go. So Pico 2 is out. That's a bit more expensive, surprisingly. What if I don't want the Pico 2? I just want the Pico. That was $380. So what? Inflation has gone up, dude. Yeah, these were like $250 each, and I bought like, I think it was 5 of them. I burned through like 3 of them very quickly by just shorting things. But anyway, thank you all very much, guys, for joining. And I hope that you've at least learned with me how to create a project in Pico and run the example code for the LCD, right? With that in mind, I'll catch you guys up on the next stream. That may be on Saturday, I think. I think Saturday we're going to stream. Another stream days. So yeah, stay tuned, and I'll see you all later. Bye-bye. Have a good night.